Welcome to this video on CFD. This video is going to be part of my series on designing an airfoil. I'm going to be using SOLIDWORKS CFD for this video, and I'm going to walk through sort of how to implement SOLIDWORKS CFD, and then how to get sort of some analytical results so that you can start to evaluate the performance of whatever you've created. So to start, what you see here is a front wing for a Formula SAE car I created in a previous video, and my goal for this front wing in this video is to get some analytical results on the lift numbers and the drag numbers. Lift in this case is going to be negative because we're looking for downforce in this application, and I'm hoping to see a fair amount more downforce than drag. So the first thing we're going to do is we're going to go into this flow simulation tab. If your flow simulation tab is not here, you should go into your SOLIDWORKS add-ons and add it. If you have a SOLIDWORKS license, you should have a flow simulation license as well. Once you have it added here, what we're going to do is we're going to go into the setup wizard. This makes it really easy. All you have to do is go into here. We're just going to give it a name quickly so that we can come back to this project later and we don't have to run it every time if we want to look at the results. So once we give it a name, we're going to click next. Here you can see it's just asking you to select the unit system that you want to be using. I'm going to use SI units just for this case. And then you can click next again. Here are some of the things you can include in your analysis. Mostly what you're going to be looking at is fluid flow is always going to be checked. And then we're going to be looking at gravity and rotation. Rotation allows you to implement something like wheels if you're doing full car CFD. We're not right now, so we will not be implementing rotation. We will be implementing gravity just for the sake of it because it does not take a ton of computational power. One thing to keep in mind is there's sort of default axes that everything works on, and they might be different to how it's set up for you. So in this case, if you look at our wing compared to our axes, you can see that gravity should be acting in the Y direction, but by default it's in the Z direction. So we're going to go and change this. We're going to make the Z component of gravity 0, and we're going to make the Y component negative 9.81. So once this is set up, you can see that we're using an external analysis type, which is good. We want to be looking at how air flows over the outside of the wing, not the inside, so that's perfect. And we're going to click next. Here's where you implement which fluids you're actually looking at. For us, we're going to be looking at gases, and then we'll look at air. All you have to do is click on air and then click add, and that automatically adds air as the type of fluid you're going to be working with. Then we can click next again. Here's where you would input the roughness of the surfaces you're working with. We're not actually going to input any roughness right now because we're just looking at sort of the basic performance of our profile. And so we don't need to add this extra complication. This is going to take longer to compute. So we can just click next, leave this alone, and this is the final page you'll see in the setup wizard. All we're really going to be changing here is the velocity of the fluid that's flowing over the wing. Again, we're going to look at a coordinate system and see that it's going to be flowing along the Z direction, specifically the negative Z direction. So you're going to go here, and you're going to want to put negative whichever velocity you want. It's in meters per second, so I'm going to put 20 meters per second, which is around 40 miles an hour, which is what we are looking for our Formula car. It's about as fast as it goes, so that's a decent benchmark to look at. Now you're going to click finish, and it will set up sort of the start of your fluid simulation. What you'll see here in this gray area is the computational domain. This is where it's actually going to be performing CFD. It won't perform it outside of this box. So what we want to do is we want to shrink down this domain to only include what we absolutely need. When we're looking at the domain, what we really don't need is we don't need much under the wing because there's not a ton of flow under because it just goes down and hits the ground. So we can make this sort of nice and close. The next thing we can do is we can bring in the sides because we're not too worried about how the air is flowing off the sides because we're not designing for it to really do so. There are some cases where there's going to be turbulent flows flowing out to the sides, but they should be pretty much equal on both sides and cancel each other out, and it's not really what we're looking at. We want to leave a fair amount of space above the wing because there is some air flowing off the top, which is interesting to us, so we will leave that with a fair amount of space. Where we do want to add a fair amount is in the front and back. You usually want to add, I would say 10 times to 15 times the length off the front, and then 20 to 30 times off the back. What this allows is it makes sure that you have nice laminar flow coming in the front, and then you allow the air plenty of time to flow over the wing and then sort of come back to atmospheric pressure and normal velocity afterwards. And this gives you sort of a full picture of how the wing is performing. The next thing we're going to want to do is we're going to want to implement a moving ground, because the way the ground moves relative to the wing is actually really pretty important. And how we're going to do this is with our boundary conditions. But first we need a plane that defines the ground. So we're going to actually go back into our sketch tree and just do our features here, and we're going to use the reference plane here, and we're just going to create this reference plane roughly where we think it's going to be relative to the ground. We're going to start with 4 inches because that's where our wing is going to live approximately. This is a realistic level of ground clearance, and so we're going to create this plane, and then what we're going to do is we're going to go into this plane and we're going to create an extruded base, and all we really have to do is make something roughly the size of the wing. This piece does not actually matter too much. All we're using it is a face to build the ground off of. So once we create this face, we can exit. We can give it an arbitrary thickness as long as we extrude downwards. You see here we're actually cutting into our ground clearance, so what we're going to want to do is we're going to move it the other way, and we can make it 1 inch. And this is going to serve as sort of the level that our ground is at. So now we can go back into our flow simulation tabs, and we can implement a boundary condition. So we're going to go to boundary conditions, we're going to right click, and then we're going to insert. What we're going to look at is the wall boundary conditions, and we're going to select the top face as our wall. We're going to call it a real wall, and then we are going to have the wall actually be moving. And so we're going to click this wall motion box. This is what we're looking for. We want to use our global coordinate system because that's easier to work with, because it's going to be the same definition as our earlier movement for the air. And so we can look into meters per second. We want it to be in the same speed, in the same direction. And so this arrow will give you sort of a nice indication of it's going to be moving like this along the z-axis. We want the ground to be moving in the same direction as the airflow, so we're actually going to make this -20 meters per second as we did earlier. The way it's moving in radians per second does not matter to us. It's not rotating, so we're just going to have this nice linear movement. Once we have the ground implemented, we can click check. You'll see these sort of little squares. This tells us that it's a boundary condition. The next thing we're going to do is we're going to implement some goals. We're going to implement surface goals, and what we want to do here is look at our forces that the wing is producing. So we're going to look at the forces in X, Y, and Z. We don't actually need to really look at all 3 because, again, the forces in the X direction that are moving out to the sides we don't really care about. We're much more interested in the drag force, which corresponds to our Z force here, and our down force, which corresponds to our force in the Y direction here. And we then want to look at where we're collecting this data from. We do not want to collect data off the ground because we really don't care about it. So for our surfaces, we want to look at everything here, all these parts of the wing, and not the ground. So if we go into here, I can believe it's this last one. That was the ground that I incorrectly selected. All right, let me just go back here. Alright, so now that we have all the faces of the wing selected and not the ground, these goals will tell us the forces that the wing is producing, but it's just the wing and not the ground. So then we can click OK, and we have these three these three surface goals implemented. The next thing we can do is we can look at our mesh. We're going to have this be automatically defining, again, because this is sort of nice and quick, and most things can have a similar mesh size. And then we're going to slightly increase the level of the mesh to make it a little bit more accurate, because what we're computing is really pretty small, and it should not take too long to compute on its own. And so now that we have everything sort of set up like this, all we have to do is go up here and click run. This will take a little bit, but we will run the CFD, and it'll probably take 3 to 5 minutes. You'll see this new tab pop up here. It'll get everything ready, and then it'll start to run through the iterations, and I will come back once this is done. Alright, so now you can see that our solver is finished. It had 135 iterations. It really didn't take too long, and so now we can go back into our part. And now that our CFD has run, what we want to do is we want to have some ways to visualize this. I'm going to go through the two main ways that I do. The first way is helpful just for sort of showing off what's going on, but it's not actually the most helpful if you want to be sort of really looking at how the wing is, how the fluid flow is interacting with the wing. This is just more of a visualization. So what we're going to do is we're going to start with the flow trajectories. We're going to put in 200 of them, and these will be equally spread throughout the computational domain. And we're going to actually go with dynamic trajectories, and we're going to decrease to 100, just because this is sort of interesting to see, but again, not super helpful. So once we have that, we're going to click select. We need to select a plane that is moving across first. We'll just select the front plane, and now if we click select, it's going to implement these, and here we can see all of the arrows represent how the fluid is flowing over the wing. And if you look at this diagram here, it shows us what the colors correspond to in terms of how much pressure there is. Again, what we're looking for is we're looking for lower pressure underneath our elements and higher pressure above, because that is what sucks the car into the ground, giving us some more grip. So you're starting to see a bit of this. We have a yellow arrow up here, which is a greater pressure, and we have a decent amount of blue arrows under here, which means sort of that lower pressure. That's really what we're looking for, so this is a good start. What you can do with the dynamic flow trajectories is you can actually watch them flow over the car. This is, again, sort of a fun thing to look at. It's good to get sort of a rough idea of what's happening, and it's a good way to show off your design. But I find for actually making changes and sort of trying to visualize what's going on in a way that's really helpful, this is not what's most helpful to me. So I'm going to stop these and I'm going to hide them. What I think is a lot more helpful is the cut plots. So I'm going to implement a cut plot. It's not going to be on the front plane, it's going to be on the right plane. And so what we want to look at on the cut plot is how this second and first element are interacting with each other. Again, this middle element really isn't doing much, so we're not going to change it for right now. What we can do is we can move this cut plot into the center of these elements, and that will tell us a bit more. So we're going to start with moving the cut plot over by 1/4 of a meter. You can see that puts our cut plot sort of back here, which is a bit odd. Let me see if we can get it to move a bit more where we want. Here we go. So now our cut plot is sort of in line with these two elements, and so what we can do is we want to look at velocity actually instead of pressure. I find it to be a bit more helpful. So we're going to select velocity here, we're going to have the contours, and then once we click OK, you're going to see it generates this cut plot. And so if you look in, you can start to see some of what we want, but this isn't actually super helpful because this end plate is in the way, so we're just going to suppress the end plate. SOLIDWORKS is going to give us some issues. Try it again. Here's that lovely noise. Okay. So for some reason it really does not want to suppress it. So what we can actually do is we can just hide the whole thing, and we can just leave behind these profiles. So we're going to want to look on this sort of straight on, and what you can see here is that the velocity is moving more quickly under these profiles than it is over the top. That's sort of exactly what we're looking for. The faster moving air means there's going to be lower pressure under these profiles, which is going to be creating that downforce we're looking at. You can see there's a bit of a higher velocity here. That's okay because it's being generated by this wing, or this second element, but it does sort of disrupt the flow over the first. So what we might look into is raising this element here higher, so that its flow doesn't interfere with the bottom element, but for right now this is sort of looking okay. The other thing you can see is that the flow is sort of stalling out in the rear of this second element, because it's coming all the way down to 0, and then we're just getting no flow. And so what we might want to do is we'll either want to make this progression a little more curved so that the air can more easily hold on, or we'll just make this element a little less steep so that the air is not stalling out here. So this is sort of what I would get away from a cut plot, and then I would go in and I would make these changes accordingly. The other thing we can look at is we can look at our goal plots. So we're going to go and insert a goal plot here. We're going to select all. Actually, we'll just select the forces in the Y and the Z directions because those are the two we're really looking at. We care a lot less about the forces in the X direction, and then we're just going to click Show. And so what this does is it gives us two values, the forces in the Y direction and the forces in the Z direction, and this is actually looking great. This is what we're aiming for, is we want a higher value in the Y direction than we do in the Z direction, because negative Z force means there is a certain amount of force pushing the car in the negative Z direction, which is backwards. This is the drag force. This is, pulling the car back, slowing it down. That's to be expected. The force that is great to see is this negative 221 newtons in the Y direction. This is our down force. This is the force being generated by the wing that is pushing the car into the ground. And you can see our force in the Y direction is a lot greater than our force in the Z direction. This is really what we're looking for, because that means we're creating more downforce than we are drag. And so this is sort of satisfactory, but what we will go do is we will sort of adjust some of these profiles so that hopefully we can get rid of where it's stalling out here and up these numbers even further.